All right, so last lecture, if you recall, we were looking at how semiconductor devices are analyzed, and we had looked at the following equations. We said there is a Poisson's equation. There is a Poisson's equation here. Poisson's equation, which is nothing but the Gauss's law, and relationship between the electric field or the potential and the electron and hole density, and the other charges that are there. And then there are these continuity equations, hole continuity and electron continuity equations, which are nothing but conservation equations. You're just counting how many electrons are there in a particular region. What can cause an increase in the number of electrons, what can cause a decrease in the number of electrons. So those are basically particle conservation equations. And then, of course, we've already seen there's an expression for electron current, there's an expression for hole current. And as we said, most of our time our interest is in calculating how the current in a device relates to the voltage applied. And if you look at the expressions for current, you see that the current depends on, there's an N here, and there is a dN by dx here. And the current depends on a P here, and there's an electric field here, and then depends on dP by dx. So what you're looking for is, to calculate current, I need N here, dN by del N by del X, I need P here, del P by del X, and del psi by del X. These are the things that I need to calculate the current. If I can find these quantities at any point X, let's say I'm doing a steady state calculation. If I'm doing a steady state calculation, it means that the same current is flowing everywhere in the device. And if at any particular point X, I know N, del N by del X, P, del P by del X, and del psi by del X, if I know these quantities, then I can calculate the current. I can calculate Gn and I can calculate Jp. I can add both of them up together, and I can get the total current flowing through the device. And how do I get these quantities here? So the goal of, many times is, how do I get these things here? Well, you have to solve these equations. Poisson's equation, continuity equation, and with the appropriate boundary conditions here. You have boundary conditions which gives us that the voltage at one end is 0, the voltage at the other end is some 2 volts, 3 volts, whatever it is. So those are the boundary conditions. So we have a framework where we have the relevant equations, we have the boundary conditions, and then if you look at these equations, you require, in order to use these equations, you require this one. You require Nd and Na, how many ionized donors and how many acceptor atoms are there, which we have seen already, how to calculate Nd plus and Na minus. You require mobility and diffusion constants, which we have already to some extent discussed. And then you require the generation recombination term. In the continuity equation that you see here, there's a generation recombination term here. Okay, so this is what we'll focus today. How does recombination in particular, how does it take place? And once we have a recombination part also, then the framework is ready. You know mobility, you know doping, and you'll know recombination also. And then you have all the relevant equations with hand, and then the boundary conditions. So you have the complete framework with you to now go ahead and look at the different devices that are there. And as I said, one way of handling this is that you numerically solve it. You forget about all the details of what these equations mean. You look upon it as a mathematical problem and numerically solve these equations, and you'll get the IV characteristics. Whichever device you want, PN junction, bipolar, MOSFET, you'll get the IV characteristics of that particular this thing just by solving these equations. That's all. Solving these equations with the appropriate boundary conditions will give it to you. And as I said, we have device simulators in which the device simulators do exactly that. Just like circuit simulators solve a set of linear equations in current and resistors, capacitors, and all that, device simulators solve these set of equations with the appropriate boundary condition. But our goal is, and goal of analysis, I keep adding that analysis is not for getting a number, but analysis is for understanding. Okay, the larger goal of analysis is to understand, and with that in mind, we would like to derive closed form expressions. We would like to go through the process of taking these equations, making appropriate assumptions, and then deriving a closed form expression for current versus voltage here. All right, so today's discussion then will focus on recombination. Okay, Now recombination, let's all right, so let's write down first the where does recombination enter. If you recall del P by del T, let's look at that. This is the continuity equation. What is the first term in the continuity equation? First term. Why does hole density in a place change? What is the reason it can change? More holes can come in and less holes go out. So the first term is that, which tells us that there is a change in current. There's a change in current with X. That can cause a change in the hole density. That's the first term. The second term is that there is a generation of holes in that particular region. And the last term is that there is recombination of holes in that region. That's it. A simple continuity equation which is there here. Now, if I look at this particular case in equilibrium, let's say if I look at equilibrium, this is 0. We said that. Equilibrium, this is 0. And current is obviously 0. There is no current, no whole current flowing. Obviously, there's no dependence on X. Which also implies that this thing here should be equal to 0. Now, what is happening, as I explained in the last lecture here, if I look at EC and I look at EV, there's a constant generation which is taking place. There's a constant generation which is taking place here because of thermal, which we call as a thermal generation. And this thermal generation is constantly balanced by a recombination process here. So there's generation taking place, electrons and holes are getting generated, and then the electron and holes are recombining also. So this GP, so in equilibrium, GP we can call it as a G thermal, right? And there is a recombination process which is also taking place, and this G thermal minus there's a recombination which is occurring, and they balance with each other. Okay. So there is a thermal generation, and then there is a recombination which occurs in this particular system. And so what we call this is a dynamic equilibrium. It's a dynamic equilibrium where equilibrium is attained because the two processes they exactly cancel each other. All right, what happens if I disturb this particular equilibrium? Okay, so for example, I could have a situation where, let's say, I have a piece of semiconductor, and so this term that you see here, I can also call this in general as a term. Let's say there's a generation and there's a recombination. So I can also call this, as a one single quantity and call it minus U. This whole thing, and I can replace it by minus U, and which we call it as the net recombination rate. Okay, which means the recombination minus the generation term. I can call this as one single variable and call it the net recombination rate. So what we are saying is in equilibrium, U is of course equal to 0. Net recombination rate. Okay, so instead of talking about generation and recombination, so what I'm saying is that you have generation, you have recombination, and the generation minus this thing is, I'm calling it as minus U. Which generation? The thermal generation. Okay, so let me explain what I'm saying is. So if let's say, what we are saying is that if I add an external input and there is let's say an extra generation rate. Okay, so what we'll have is, our equation will become, if you would like, del P by del T minus 1 over Q del JP by del X plus, let's say this is external, G external, plus now remember there's a G thermal generation which all the time occurs, and then there is recombination. Right, I can write this as, there's always a thermal generation which is taking place, and this is the external generation rate. It could be light. I could shine light on my semiconductor and thereby generate photon. Okay, so G thermal minus R is what I'm calling it as the net recombination rate. Okay, and this thing is a external generation rate. Okay, So this continuity equation can then be written as del P by del T minus 1 over Q del JP by del X plus external generation rate. Leave aside your thermal generation rate. G thermal minus R is what I'm calling as a minus U. So what I'm going to do today is derive for you a expression for U. What is this recombination rate? Okay. All right, so the recombination, so this thing that is there here. So what we are talking about is, of course, very simply, there's an electron and there's a hole. The two are recombining together. Now, the recombination can take place due to various mechanisms. There's various ways in which electrons and holes can recombine. And in silicon, the dominant mechanism for recombination is what we call as SHR recombination. The names of these people who first described it, Shockley, Hall, and Reed. Shockley, Hall, and Reed recombination, SHR recombination. That's the dominant recombination mechanisms. Once you understand that, then the other mechanisms we'll talk about a little later on. Those are not as important. Now, this Shockley-Hall-Reed recombination that takes place, it takes place via a defect level. There is a EC here, and there's an EV here, and there is a defect level. In a perfect lattice, you have only conduction band and you have valence band, and then the gap in between, we call it as a forbidden gap. There are no states within the gap. But when you add distortion in the lattice by maybe adding impurities, or maybe there are some native defects in the lattice, then what happens is these defect levels appear. We've already seen that if you add donor atoms, then you get a level very close here. Remember, you get a level very close to the conduction band. If you add donor levels, and we call it ED, the donor level here. Or if you add acceptors, you get these levels here close to it. You may call it EA. Now, these are called, if you look at ED and EA, they go by the name. These are shallow impurities. Shallow, why? Because they introduce a defect level which is either close to the conduction band or very close to the valence band. Shallow impurities. What we are talking about today, these shallow impurities, you will see, at least qualitatively understand, these shallow impurities, they do not play a big role in recombination. Recombination occurs due to a defect level that I've shown, which we also call as a deep level. Deep level is deep into the energy gap. The distance, the gap energy between the defect level and conduction band or valence band is large. Now, how large? For example, a defect level could be right in the middle, about 0.5 eV. Silicon band gap is about 1.1, 1.12, so it's roughly in the middle, okay, in the middle of conduction and valence band. So recombination, when we are talking about recombination predominantly occurs due to deep levels. And it's sort of, you can understand even at this outset why a deep level would contribute to recombination rather than a shallow level. You can understand that if you look at a donor level, the donor level, you can see electrons here going to the conduction band or an electron falling back into this. A donor level interacts strongly with the conduction band. And the donor level's interaction with the valence band is weak. Okay, so donor, that's why we call it donor. It just interacts with the conduction band. It either gives an electron to the conduction band when it ionizes, or if the temperature or whatever is not enough, the electron will fall back into the donor level. So it's primarily interacting with the conduction band. And acceptor level's interaction is with the valence band. But recombination, you understand, in recombination, what you have to do is, you have to interact both with the conduction band and with the valence band. You're trying to recombine the electrons and the holes. So you need a level which can equally well interact with both the bands here. And such a band, you would naturally understand, would be, let's say, equally away from conduction or the valence band. It's not very close to the conduction band, then it would be primarily interacting with the electron. It's not very close to the valence band, then it will be primarily interacting with the holes. Somewhere in the middle, then the interaction between both of them may be comparable, because it has to act as a recombination center here. Okay? So it's the deep levels which are important for us, not the shallow levels, not the donor levels, not the acceptor levels, but it's a deep level which is important for recombination. All right, so how does this, so let's focus on the deep level then. So this is our EC, and this is our EV. And let me, now the deep level could be, as I said, it's deep, but it could be, at any energy. So for simplicity, what I'm going to do is I'm going to assume it right in the middle. Okay, just for simplicity. Now what I would do is, so this is the defect level. Let's call this ET or defect level, and it's at, I'm just assuming it equal to be EI, right in the middle. Okay, just for simplicity. There's no, ET could be above EI, ET could be below EI. As I said, it's likely to be close to EI because it's in the, it's deep and it's equally away from, let's say, many times from the conduction and the valence band. What I would suggest, I'll do the derivation today assuming ET equal to EI. As an example, as a homework, do the derivation again by yourself. You'll understand things better by assuming that ET is a general term. Okay, so you'll go through all these steps and derive a new expression with ET there in it. Okay, and so that would help you to see. All right, so now when there is a deep level, what are the things that can happen with a deep level here? Okay, so let's look at this deep level. A deep level can, obviously for recombination, we're assuming there are electrons there and there are holes there. So a deep level can, what it can do is it can capture an electron. Let's call this process number 1. Capture an electron. An electron is there in the conduction band and it captures it. A deep level can also emit the electron back to the conduction band. Let's call this process number 2. So it can capture an electron, it can emit an electron back. Or what can happen is it can capture a hole. 3. It can capture a hole. And obviously it can emit it back. It can emit a hole back to the valence band. So it's doing all of these things. It can capture an electron, it can emit it back. It can capture a hole and it can emit it back. So it's capable of all these things here. All right. What will lead to recombination? Can you see what process will lead to recombination? A recombination. Recombination would imply a recombination. You can see how it will recombine. Well, it may capture an electron. It may capture an electron, say 1, process 1, followed by 3, followed by 3. An electron, remember, capturing a hole actually means what? It's advisable not to think of valence band in terms of electrons. As I said, once we have said all the electrons in the valence band, collectively, their effect can be modeled in terms of holes. Okay, so it is advisable not to think of, valence band, there are electrons and all that. Okay, but just for a moment, if 1 means capturing an electron. And what does 3 mean? Capturing a hole, but effectively it means that the electron is going from the defect level into the valence band here. So that sort of leads to recombination, or vice versa. This can happen this way also, right? Capture a hole, followed by capturing an electron. Right? So these processes result in recombination. What will cause a generation? What will cause a generation? 2 and 4 will cause generation. You end up generating an electron and a hole. So these defect levels, they contribute both to generation and to recombination. What if the following thing happens? If let's say, so 1 and 3, as I said, if 1 is followed by 3 or if 3 is followed by 1, we have a recombination event. The electrons and holes disappear. What if we get 1 and every time you get a 1, The 3 and 4 are weak. So what you get is 2, maybe. Or from 2 to 1. If this is the dominant process, what is that? That 3 and 4 are not dominant, very weak. 3 and 4 are very weak. So what happens is, one may happen, you may capture an electron. The electron may sit in the defect level for a while, and then it may emit it back. So, and the interaction with the valence band is very weak. 3 and 4 are very weak. So what does my defect level act? It acts as a trap. My defect level acts as a trap. It momentarily traps the electrons. Traps it, why? Traps it in the sense that particular electron is no longer available for conduction. Because once the electron is in the defect level, it's not conducting, it's just localized. So it acts as a trap. If 1 and 2 are dominant, if you capture an electron, and the next most likely event that may occur is you release it back to the conduction band. 3 and 4 are not occurring. So we call it an electron trap. Or you may have 3 occurring and 3 followed by 4, and these are dominant. So you may call it a hole trap. You may call it a hole trap, you may call it an electron trap. So you can see that what may happen is, if you introduce a defect level, it may act as an electron trap, that 3 and 4 are very weak. Or you introduce a defect level, 3 and 4 are strong, 1 and 2 are very weak events. And so it acts as a hole trap. So what we are looking for is a defect level for which 1 is strong, 3 is strong, and predominantly it acts as a recombination center. Okay, so how do we now, remember what our goal is to, qualitatively we know that a defect level can do all this, but what we would like to do is get an expression for U, the net recombination rate, in the absence of any external generation rate, okay? So we want a net recombination rate, we want to get an expression now. An expression you would obviously think would depend on what? What are the things that recombination rate would depend on? To start with, what are the variables that would enter? What do you think? Obviously, N and P. Electrons and holes are recombining. If I have more electrons and more holes, more recombination will take place. That's understandable. N and P. What else? Temperature, okay. Temperature, okay. Fermi level, N and P sort of, it's net recombination is taking place. I have non-equilibrium situation. And N and P are related to Fermi level. So either you say NP or you say EF and EFP. It's the same thing. There's no extra information. Right? So, EF and EFP are there. Obviously, the defect characteristics. How does it capture? How does it capture an electron? How does it capture a hole? That's what I'm trying to tell you is each defect level is not the same. Some defect level may act as a trap only, electron trap. Some defect level may act as a hole trap. Some defect level may act as a good recombination center. Some may act as a poor recombination center. So obviously, in here should enter all the defect characteristics. Some may, obviously it should depend on what is the number of defects. If I have more number of defects, it's more likely that my this defect level causes recombination. If I have less number of defects, note that if I have large number of defects, there's a greater probability that I'll capture an electron. And there's a greater probability that I'll capture a hole if I have large number of defects. If I have less number of defects, there's less probability. So obviously number of defect levels is very important here. But there's something else. Now what we need to do is go back and look at these processes in a little bit more detail. What do I mean by capture? How do I characterize capture? Okay. So let's look at this particular process here. Let's focus on, there is a defect level here, EC. And you recall that let's focus on process 1 and 2. Process 1 and 2. Okay? Because whatever I say about 1 and 2, same thing is about holes. Capture of holes and emission of holes, those are similar. So once I understand capture of electrons and emission of electrons back, then I know 3 and 4 also. Okay? There's similar process here. So capture of holes. So one is capture of electrons. Okay, capture of electrons. How do I understand capture of electrons? How does a defect capture an electron? In order to understand that, it would make sense to you. Let's say if I have a defect somewhere in this thing here, you would understand. It would make sense to you that let's say if I draw a certain area around it, and if I say if an electron ventures into that particular circle, it will get captured. Does that make sense? If an electron ventures close to, obviously if the electron is very far from my defect here, whatever this defect is, if an electron is very far, well, the defect doesn't have much influence over it. What we are saying is there's a radii of influence of a defect that is there. If the electron happens to be, get into that particular one, into that circle, it will get captured. So what people define is what we call a area of capture cross section, sigma. So capture cross sectional area, we define that. If it gets within that, we say it will get captured. There are, for example, a simple way of conceptualizing, let's say, a defect could be like this here. So, I could make like this. These diagrams, you guys recall a diagram like this? Where have you seen hydrogen atom? Remember hydrogen atom, how you draw? There's a nucleus there, and then there is this electrostatic potential which is there here, right? 1 by R kind of a potential. So it goes like this here. So imagine if an electron, if we think of a defect like this, a defect is an atom, let's say it's an impurity. For example, one defect which acts as a very good recombination center is gold. Now, why would you want to add a precious metal gold to silicon? That's a different matter. But gold in silicon acts as a very good recombination center. Okay, so for example, gold which is there. So if I add gold to silicon, and it has been widely studied, effect of gold in silicon has been widely studied. Okay, so for example, if I add a gold there, gold is an atom which is sitting there in my silicon lattice, and being an atom, you would think that it has some nucleus and some electrostatic potential around that and all. So you can imagine that if I have an electron here, well, this is far from this particular nucleus, doesn't have this thing here. Sorry, doesn't have. It's not under the influence of the defect. But if the electron happens to be here, what is likely to occur to it? Well, there's an attractive force. This is going to get sucked in, right? It's going to get sucked in, and whatever happens, then the gold captures it and all that. So what we are saying is there is a range of influence of a defect level, and that is being characterized by capture cross section. And so it has units of area, centimeters square. It has units of area, centimeters square. Now you may be wondering, how large is that area? What do you think is the area? Would be an area. Capture cross section, a typical value. We're talking about an atom and a sphere of influence where it would capture. You want to take a guess? 10 to the power minus how much? Say one value, okay, you're right. 16. 10 power minus 16, let's say, is one number. I think for gold, when gold acts as a defect level, the capture cross section, so just to get an idea, the capture cross section is, the area is 10 power minus 16. So 10 power minus 16 centimeters square. All right, that's the number that you can keep in your mind. All right, so now that we know that, okay, so this defect level is there. So the defect level now, and by the way, I should add this as sigma n. This is the capture cross section for electrons. Similarly, there'll be a capture cross section for holes. Okay, so let me add sigma n. So now, what do you think is the rate of this? What is the probability that my defect level, probability that a defect level captures an electron? What would it depend on? Do you think it would depend on sigma? Obviously. Sigma, obviously sigma. What else will it depend on? Probability that my defect captures the electron. It would depend on how many electrons are there. Right? It would obviously more electrons, then more probability that it captures. So you would think that it should depend on n also. What else will it depend? The probability that a defect captures the electron. No, the probability that a defect A defect captures the electron. You're right, total capture rate will depend on that. The probability that a defect captures an electron would depend on sigma n, would depend on n. What else? Now remember what is happening with the electrons. So if I were to think about my lattice is there, of course, and you know that silicon atoms are there, all this, whatever, the lattice is there. And somewhere there's a defect sitting there, here, right? And the electrons are moving around. Electrons are moving around. Now, an electron has to come close to the defect to get captured, right? If the electrons were not moving around at all, what would happen then? Let's say the electron was not moving at all. Would any capture take place? No capture will take place. If the electron is rapidly moving around, you think there's a greater chance that, is going here, there's a greater chance that it may end up next to a defect level. So is it pointing out that maybe the thermal velocity, the velocity with which the electrons are moving around, will that play a role? If the electrons are moving around rapidly, maybe there's a chance that it will get close to the defect and will get captured. If it's not moving at all, it's just sitting there at one place, well, and there are very few defects. Remember the defect, what is the defect density that we are talking about, by the way? Capture cross-section we have written. A defect density that we are talking about, let's say, is 10 to the power 12. 10 to the power 12. Remember how dilute this particular system is? Number of atoms that we are talking about silicon is 10 to the power 22. And number of defects that we are talking about is 10 to the power 12. We're talking about 10 orders, this thing. So very, very few defects are there. We're talking about extremely few defects. So unless the electron is moving around and all that, it's not going to get close to a defect and get captured. So the other thing is probably the velocity with which electrons move will also play a role. If they're moving faster, we think that there's a greater chance of. Now, how do we knit it together? How do we put all these things together? We know that capture cross-section is there. We know number of electrons that are there. We know VTH is there. All these factors are there which will affect it. Now, how do we put it together to say capture rate? Capture rate. So, for example, capture rate, let's say I want to write it like this. dNt by dt. All right, so it doesn't take it. dNt by dt. What does it mean, dNt by dt? Nt is the number of electrons in the defect. Number of electrons which have been captured. The T refers to that. When I simply write N will refer to number of electrons in the conduction band. P will refer to number of holes in the valence band. Nt refers to number of electrons in the defect state. T, ET. The trap level or defect level ET here. So the number of defects, so the rate at which the electrons are being captured is what I'm talking about. Capture rate, the process, the rate at which it is being captured. dNt by dt. Obviously, it would depend on sigma. Okay, so it would depend on something here. And it would also depend the rate at which it is being captured now, the number of electrons that are there in the defect state and the rate at which it is changing would obviously you would think it will depend on Nt 1 minus, let's say, Ft. Who can capture a defect? A defect which is empty, right? A defect which is empty, because remember, once a defect captures an electron, it will acquire a charge. The probability that it will capture one more electron is not possible, because it becomes negatively charged, let's say, and then the other electron will not try to get close to it, right? So the who will capture this is the total defect density, and 1 minus Ft refers to the fact, Ft is the probability that the defect is occupied by an electron. 1 minus Ft refers to what? The probability that the defect is empty. Okay, so Ft is the probability that a defect is occupied with an electron. Okay, so obviously it would depend on this. If I have all the defects which are full of electrons, then no more are going to be captured. Okay, so dNt by dt will depend on nt, 1 minus ft, plus all these things that we said about. Sigma, n, Vth, all of those things, things that are there that will enter into this here. Okay. All right, so let's look at the capture. Let's see if the capture process makes sense to you. The way people think about how the capture is taking place, as I said, this is a capture cross-section. So we said that the electrons are moving around. You know, we have a, let's say, a defect here. And we said that the electron is moving around like this, or whatever, and happens to get close and gets captured. Right? Within it enters the capture cross-sectional area and gets captured. That's how the electron is moving around. Now, can I model this process slightly differently? In the sense that instead of saying that the electron is moving around, suppose I say the electrons are all fixed. The electrons are all fixed and the defect is moving around. The electron is all fixed and the defect is moving around. Would it be something similar? Sort of relative motion? Instead of saying electrons is moving around and comes close to the defect, what if I say, well, let's say the electrons are all there. The electrons are all there, the defect is moving around. The electron is moving with what? With a velocity Vth. We call it Vth, why? Because it's the velocity due to thermal energy, Vth. The electron is moving around with Vth. Now suppose I say, well, the electrons are all there, and my defect is moving around. Defect is moving. So if you take that particular picture, if the defect is there and it has a cross-sectional area sigma, in 1 second, how much area will it, how much volume will it cover? It has a cross-sectional area. Do you realize, let's say it's moving in certain direction, so it will go like this, let's say. And the total volume that the defect will sweep is sigma times Vth. Correct? This sigma is the cross-sectional area and it moves and it sort of covers a volume sigma Vth. Now what we are saying, why sigma Vth? We are saying if an electron is there inside that volume, it will get captured. And how many electrons will be there in that particular volume? Remember what is n? N is the number of electrons per unit volume. How many electrons are there in this? This is the volume, right? Remember, this is centimeter square, and this is centimeter per second. So this is the kind of volume that is there. And if we multiply it by n, we'll get the probability that the electron, probability with respect to time that the electron gets captured. N is the total number. Electrons are distributed. Sigma Vth(n). So this is what we're calling it as the capture rate. So what we are saying is that the rate of capture will depend on sigma Vth(n) multiplied by nt 1 minus ft. The rate at which the electrons are getting captured, or the rate at which my electron density in the defect state, the rate at which it is rising. This is the capture rate. Sigma Vth(n) and nt 1 minus ft. Nt is the number of empty traps, a number of empty defects. Number of empty defects. Number of empty defects. Note that as you can see here, sigma Vth(n) has units of 1 over second. Has units of 1 over second. This is concentration, and therefore it tells us the rate at which the number of electrons in the defect level, the rate at which it is increasing. The total rate at which it is capturing the electrons from the conduction line. Okay? Yes?
So why the n?
Which one? N?
Sigma Vth(n).
Why n?
Yes.
So what we are saying is the capture rate would depend on, we are saying that the defect is moving, and this is the critical area sigma, and so it sweeps out a volume sigma VTH, and if in that volume a electron lies, then it will get captured. And number of electrons per unit volume is n. So n multiplied by that particular volume gives us the. So sigma VTH n then decides the capture rate. And the total number of electrons that are getting captured would then depend on the capture rate multiplied by how many empty defect states are there. So capture rate multiplied by empty defect rate. So if you would like, I can call this Cn, capture rate, multiplied by the number of available empty defect states. All right? Okay? Now, let's come back to our diagram here. This is process number 1. But this is also occurring, right? Process number 2 is also occurring. So, right now, when I wrote dNt by dt, and I wrote sigma and VTH n, and I wrote nt 1 minus ft, I wrote only about the process number 1 that is getting captured. But 2 is also occurring. 2 is also occurring. Once the electron gets captured, well, it may get emitted back. So what is the net capture rate? This is only talking about the capture process. The net capture rate would be 1 minus 2. That would be the net capture rate of electrons. Okay, right now this is just modeling the capture process here. So the reverse process, see if it makes sense. The emission of electron back to the conduction band, what will it depend on? First of all, it will depend on the fact that the electron exists in the defect state, which is Nt into Ft. Agreed? These are the defect states which are occupied by electrons, Nt into Ft. And then we call this as the emission rate. Emission rate, the rate at which is emitting. You remember this was the capture rate, Cn, and we add the emission rate here, En. En is the rate at which is emitting back. Whatever this En is, we don't know what En is, but we write it as En. Some emission rate. So just like we wrote some capture rate here, for capture rate we could write the expression sigma VTH n, and here is the emission rate, En. Okay, no problem. Emission rate. Now emission rate would naturally depend on the nature of the trap, nature of the defect here, that is there here. Now we can obtain an expression for En also. How? Well, suppose I look at equilibrium. In equilibrium, what do you think will happen? In equilibrium, the rate at which it is getting captured equals the rate at which it is emitting back. That d1 and 2 cancel each other. So equilibrium implies dNt by dt equal to 0. The two are equal to 0. So what we can do is then we can write sigma n, VTH n. Let me write n0, n. So this is there, n0, nt. 1 minus ft is what? Ft is the equilibrium probability distribution function. So we can use the Fermi-Dirac probability distribution function that tells us how a particular state is occupied. So 1 minus f. This is the Fermi-Dirac function here. Equilibrium, let's call it 1 minus f0. This is equal to nt, f0, en. So nt cancels. And then we need to write down what is f0 here. So we can write this as En equal to sigma n, VTH n, n0, 1 minus f0 by f0. n0, 1 minus f0 by f0. That's the emission rate. Now, what is, we can write down now this thing. Okay, So emission rate is En is sigma n VTHN N0 1 minus F0 by F0. Now what is this F0? F0, if you remember, was the probability that the defect state was occupied by an electron. So F0 we can write as 1 by 1 plus e to the power, this is the defect energy ET minus EF by KT. That's the probability that the defect state, which lies at an energy ET, is occupied by an electron. So F0 is that. Now, this is where, as I said, I'm going to make an sort of an assumption. I don't need to. There's nothing. The assumption that I will make is ET equal to, it lies in the middle. ET equal to EI. And from there on, as I said, you will do a homework assignment where you'll assume a general and carry on the derivation. Okay? So ET equal to EI. So what is 1 minus F0 by F0? What is 1 minus F0 by F0? What will that give us? E to the power? ET is EI minus EF, right? By KT, correct? It will give us that. ET after substituting. What is N0 here? N0 is Ni e to the power what? EF minus EI by KT. Recall this expression. So now you will take this and multiply. What do you get? En equal to sigma n VTH n multiplied by Ni. Sigma n VTH n Ni. Emission rate. So now what we are saying is, if I know the capture cross section, and we've already assumed the energy ET, okay, ET equal to EI, then I know, so all that you need to know is the capture cross section, sigma, and you need to know the energy of the defect level, and then En then is a function of the remaining. En is not an independent variable. En can be determined from sigma, VTHN, and Ni. Can be determined from that. Okay, so there are two. We are characterizing a defect level in terms of three important parameters here: ET, sigma, and sigma, of course, would be there sigma n and sigma p for both of them, ET and NT. This is how we are characterizing, and we are saying with these we can determine the capture rate and the emission rate and all of that. That is there. Okay. All right, so if we go back, then what will be the net capture rate that we can write down? Note that this is the net rate at which the carriers are getting captured. Okay, so we are running out of time. So net capture rate, as you can see here, we can substitute En, the expression that we just obtained, right? So En would be whatever sigma VTHN, so it's the same, sigma VTHN, and here Ni. Yeah.
So we calculated even for an equilibrium situation.
For equilibrium situation, we are saying that in non-equilibrium also the rate at which the defect emits, the emission rate, even if it's non-equilibrium, is the defect which is emitting it back. It remains the same. Whether you have less electrons or more electrons, the number of electrons which are there in the conduction band are in any way very small. So it doesn't really matter. But the probability of emission from the defect, the emission rate remains the same. So now note that what will happen is the following. So we have a general expression for now the rate at which the electrons are getting captured. dNt by dt is sigma VTH and n, nt 1 minus ft, nt ft, and En is sigma VTH and ni. Sigma VTH and ni. Okay? Now in non-equilibrium, I don't know what ft is. Okay? Please remember. In equilibrium, I could write it as f equal to 1 over 1 plus e to the power e minus ef by kt. In non-equilibrium, I don't know what this is. Okay, so the next thing that I'll do is, as you can imagine, the next thing that I'll do is I'll write down a similar expression for dpt by dt. I'll write down an expression for the rate at which the holes are getting captured. Exactly same process I will follow and write down that. And when recombination is taking place, what is really happening? When recombination taking place, what is really happening? That the rate at which the electrons are getting captured is equal to the rate at which the holes are getting captured. So I'll write an expression for here, write an expression here, and then I'm going to equate these two together. And I'll say these two are same, equal to the rate at which electrons are getting captured and the rate at which the holes are getting captured. Both are the same. So once you write an expression like this, and once you write an expression for similar expression, equate the two. Because in steady state, electrons are getting captured, holes are getting captured, and they're annihilating each other. And so you equate the two together, and what you end up getting, let me see. What you end up getting is an expression like this. The net recombination rate that you see. NP, Ni squared, tau NP plus Ni, slightly more general expression. So what I would suggest is the following. Go ahead and try to derive now. Fill in the gaps and try to derive an expression yourself and see what you get. Okay, in what you will have to do, if you go back, note that what you'll have to do is you will equate these two together, and as you equate, you'll get an expression for Ft. What is Ft? Because you'll take this term and you'll take another one, equate it together, you'll get Ft. Once you get an Ft, you put it in this particular term back again, and you'll get the net rate at which electrons are getting captured, which is the net rate at which recombination occurs, and you'll get an expression for recombination. Okay, so follow through with the process, and we'll try and complete the discussion in the next lecture.